Welcome back to Arxflix. Today, we're diving into a fascinating paper titled EMO, Emote Portrait Alive, Generating Expressive Portrait Videos with Audio2Video, a diffusion model under weak conditions. This research tackles the challenge of creating realistic and expressive talking head videos, focusing on the dynamic relationship between audio cues and facial movements. The EMO framework, as shown here, takes a single reference image and audio as input, generating expressive portrait videos with varying head poses and durations. Let's explore the key aspects of this paper. Traditional methods often struggle to capture the full spectrum of human expressions and individual facial styles. They rely on constraints like 3D models or facial landmarks, limiting the naturalness and richness of the generated expressions. EMO proposes a novel framework that utilizes a direct Audio2Video, a synthesis approach, bypassing the need for intermediate representations. This ensures seamless frame transitions and consistent identity preservation throughout the video, resulting in highly expressive and lifelike animations.
Here's a breakdown of EMO's architecture. It consists of two main stages: frames encoding and diffusion process. The frames encoding stage extracts features from the reference image and motion frames using ReferenceNet. The diffusion process stage utilizes a pre-trained audio encoder to process audio embedding, integrates facial region masks with multi-frame noise, and employs the backbone network for denoising. The backbone network incorporates reference attention and audio attention mechanisms to preserve identity and modulate movements, respectively. Temporal modules are used to manipulate the temporal dimension and adjust motion velocity.
Let's delve into the key components of EMO. The backbone network, based on the ANET structure of Stable Diffusion 1.5, denoises multi-frame noise latent inputs to generate consecutive video frames. It incorporates temporal modules for frame continuity, reference attention, layers for identity preservation, and audio attention and layers for motion modulation. Audio layers encode voice features from the input audio sequence using Audio2Video, capturing pronunciation and tone. These features are then injected into the generation process through audio attention layers, influencing the character's motion. ReferenceNet, with a structure similar to the backbone network, extracts detailed features from the input image. It ensures that the generated video maintains the identity of the reference image. Temporal modules, inspired by Animate Diff, apply self-attention temporal layers to capture the dynamic content of the video, ensuring smooth and coherent frame transitions. To ensure stability and controllability of the generated motion, EMO utilizes a face region mask and a speed controller. The face locator encodes the bounding box mask, guiding the generation of the character's face. The speed layers incorporate head rotation velocity information, synchronizing the speed and frequency of the character's head movements across different clips. EMO's training process is divided into 3 stages: image pre-training, video training, and speed layer integration. This staged approach ensures effective learning of the model's various components. EMO was evaluated on the HD-TEF dataset, demonstrating superior performance compared to existing methods like Audio2Lip, SadTalker, and DreamTalk. The results were assessed using metrics like FIDE, SyncNet, FSIM, and FVD, showcasing EMO's ability to generate high-quality, expressive, and identity-preserving videos. Here's a visual comparison of EMO's results with other methods. EMO outperforms existing methods in generating a wider range of head movements and more dynamic facial expressions. EMO demonstrates its ability to generate talking head videos for diverse portrait styles, including realistic, anime, and 3D characters. EMO excels in generating richer facial expressions and movements when processing audio with pronounced tonal features, like singing. EMO outperforms diffused heads in generating high-resolution videos with minimal error accumulation across frames. EMO achieves significantly lower FVD scores, indicating superior video quality. It also outperforms other methods in terms of individual frame quality, as evidenced by improved FID scores. While not achieving the highest SyncNet scores, EMO excels in generating lively facial expressions, as shown by the EFID metric. EMO has some limitations, including its higher computational cost compared to non-diffusion-based methods. Additionally, the lack of explicit control signals for body parts can lead to artifacts in the generated videos. That's a wrap on EMO. This research presents a promising approach for generating expressive and realistic talking head videos. If you're interested in exploring this further, check out the paper linked in the description. Don't forget to like, subscribe, and share this video with your fellow AI enthusiasts. Until next time, keep learning, keep exploring, and keep creating. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.